And good evening, everyone. We're now live in YouTube, LinkedIn, and Facebook. So once more, welcome in a few minutes. About to begin data acquisition and LabVIEW for test engineers. Let's now add our sharer for this evening. Let's say hi.
Hi, good evening.
Great audio, Sir Lawrence. Yun. Good evening, Sir Lawrence. What do you have in store for us this evening?
so this evening we're going to be talking about data acquisition and LabVIEW. I'm going to go through some of the basics, overview, and you know, tonight, they will learn a programming language that is different in nature. It's graphical. So I'm excited to share it with you guys. Thank you, Sir Joe Mark, and especially for your team for inviting us today to discuss about engineering, especially on a rainy Friday. I think it's raining outside. Yeah, it's quite cold tonight. So yeah. Anyway, thank you, Sir Joe Mark. So I created this session for beginners and also for engineers who want to refresh their knowledge of data acquisition. So by the end of the session, I will also share programming language that will help you acquire, analyze, and visualize your data. Okay, I also have a demo right here. I'm not sure if you're going to see it. Maybe I can switch a camera later on. It's a hardware that will allow you to acquire data. All right. So first, I'd like to thank all of you for spending your weeknight with me. I'm going to try my best to make it the most of your time, because I think that's the most important thing for us, right? Time. Okay, and then I'll send you off to your weekend sleep. Okay, so by the way, as introduced earlier, I'm Lorenz Yatco. I'm an engineer by profession and a photographer as well as a videographer by passion. Actually, me and my wife, we were quite active in the social media stuff. So if you want to follow us, you can follow my wife for mom stuff, travel stuff. But if you'd like to learn more about technology, some tips and tricks, I do that as well. So my page is starting a bit, but feel free to type it in or follow me anywhere on that. All right. So while we're on that topic, actually, we also have another conversation with Sir Joe Mark and his team in CAD Community Asia and Digital Creatives Worldwide. We are planning a photography tutorial for beginners. Right, Sir Joe Mark?
Yep, extremely excited for that as well.
Yeah. So in this one, I think, as I mentioned, this is also my passion. I can take you through the basics first, and then maybe we can go a little bit more advanced. So yeah, without further ado, I would like to get started with our agenda for today. So, for today's agenda, we are going to briefly touch on the following topics, but it's not an in depth session, it's just more of an overview. So we'll tackle the essential concepts or the three R's of data acquisition. So by the end of this, you should know what are three R's. You're also going to talk about signal conditioning basics, as well as a graphical programming environment, which is LabVIEW. And I'll just give you uh, a little bit of introduction of who I work for as of this moment. All right. So yeah, let's get started. By the end of the session, if you have any questions or maybe somewhere in between, please feel free to type it in. I'm not seeing the questions, but I think Sir Joe Mark and the team will help us, bring that up into the screen. Right? Yeah. Okay.
Absolutely.
Thank you. All right. So first of all, for those attending, I think most of you are test engineers, or automation engineers, right? Are you familiar with sensors? So probably yes, right? So since we're drilling down to the basics, we're going to talk about sensors at the very base level. So sensors could be vibration sensors, torque, displacement, temperature, force, strain, or pressure, right? So back in the day in the factory, we would have an engineer or technician install this and watch the response of these sensors manually. We are monitoring vibration, temperature, and if something happens, another engineer will probably turn on a valve, shut down a something system. And this is why engineers started to develop control systems, right? You've been hearing about PLCs or programmable logic controllers, SCADA, distributed control systems. So these have been developed to acquire data, set limits, and submit data to servers. And of course, its main goal to control. Okay. So while most of these previous systems depend on analog gauges, the Industrial 4.0, I think you've been hearing about the Industrial 4.0 or the Internet of Things, is slowly revolutionizing the factory of the future. And this is why we need to have a way for these automation systems to be at least connected to the computer. Okay, and that's what I'm going to share with you today. I will also give you a demonstration on how to acquire a temperature from a sensor, from a very basic sensor like this, and then program it graphically. So the one you're seeing on the left side of the screen is your user interface, while the right side of the screen is your graphical programming language. We'll talk about more of this later. Okay. So, as I mentioned, let's talk about the basics of that. So, when I say DAQ, it means data acquisition. So, just to get started, right? So, the question is, how do you get a utilized data acquisition system without spending thousands of dollars or pesos on equipment? First, I do have a question for you. Have you ever been in a situation where when you buy something and only use 10% of it? So I think, well, most of us should be in the same situation. We buy phones that are overkill, I would say, but we only use a fraction of its capability. When we build data acquisition systems, it helps to be informed. You have to, at the very least, you have to know what are the basics of the data acquisition system so that you know what options are available for you. And that's why we are going to start defining them today by understanding your channel counts and knowing your base specifications. Okay, so there are three main components of a DAQ system or a data acquisition system. First is the sensor. The sensor converts a physical phenomena into a measurable electrical signal. Examples of this would be flow meters, thermocouples, pressure sensors, accelerometers, and many more. Those that you've seen earlier. Now, to connect this to your computer, you need the second component, the data acquisition device. The data acquisition device basically digitizes an incoming analog signal so that a computer can interpret them. So it has two parts. First is the signal conditioning. Signal conditioning manipulates a signal into a form that is suitable for input to an analog to digital converter or an ADC. Okay? So an ADC provides, once the analog input comes into the ADC, it provides a digital representation of the analog signal at any instant in time. So we're going to talk about more of that later, more specific, because it's the basics. Then, of course, you'd have to think about the bus. The bus is what connects your data acquisition device to your computer. It's basically your USB, your Ethernet, your Wi-Fi, or your Thunderbolt. Now, down to the third component, the computer, which basically controls the operation of the data acquisition device and is used for processing, visualizing, and storing measurement data. Now, you can divide your computer into, or you divide this into two parts. The driver software, which provides the application software the ability to interact with your DAQ device, while the application software facilitates the interaction between the computer and you for acquiring, analyzing, measuring, and presenting data to you. So we'll talk about the stuff on the right once we've finished the basics. So for now, let's refresh our memories on the signals we're measuring from. All right. So the signal that is produced by a sensor can fall into one of the two categories, either digital or analog. So the type of signal we're trying to measure will affect the way on how we will measure it. So it is important to understand the differentiation between the two of them. So what we have here is a digital signal. A digital signal only has two states, either on or logic high or off or logic low. An example of a digital signal is a TTL signal or a transistor to transistor logic signal. The specifications for a TTL signal state that a voltage between 0 to zero point 0.8 volts is considered logic low, while the voltage between 2.2 to 5 volts is considered logic high. Now, the area between zero point 0.8 and 2.2 is considered indeterminate and could be interpreted as either a logic high or a logic low. So make sure that your signal doesn't fall into zero point 0.8 to 0.8 to 2.2 because you might not know whether it's really high or low. Okay? So most digital devices in the industry accept a TTL or transistor to transistor logic signal. So this also includes the digital lines on most data acquisition devices, which will accept and generate TTL compatible signals. Now, since a digital signal only has two states, we can only measure two quantities of a digital signal: state, whether it's high or low, and rate, which is the number of transitions up high to low, low to high in a given amount of time. Next, let's examine the characteristics of an analog signal. Unlike a digital signal, which contains only two possible states, an analog signal can be at any voltage 0.2, 0.4, 0.6, or somewhere in between at any point in time. So an analog signal can be any voltage, right? Since an analog signal can be at any state at any time, the physical quantities we want to measure differ from those of a digital signal. So what are those quantities, right? Or those types of measurements? So there are three quantities that may be of value. We can measure the level, the frequency, or the shape. So measuring the level of an analog signal is similar to measuring the state of a digital signal. The only difference is that an analog signal can be any voltage, not unlike digital, it's 1 or 0, right? Okay. Shape. Because analog signals can be at any state with respect to time, the shape is often important. For instance, we have a sine wave and a sawtooth wave. Measuring the shape of the signal opens door to further analysis on the signal itself, such as peak values, slope, integration, and many more. Now for frequency. Measuring the frequency of an analog signal is similar to measuring the rate of a digital signal. However, you cannot directly measure the frequency of an analog signal. That's why you need software analysis to extract the frequency information. This analysis is usually done by an algorithm called Fourier transform, or FFT or FT. Okay. Now, now we're done identifying digital and analog signals, right? So let's identify the first item of your data acquisition system, the sensor. As we have mentioned, the sensor converts a physical phenomena into a measurable electrical signal. So sensors convert physical phenomena such as light, temperature, pressure, position, sound into a measurable electrical signal, such as a voltage or current. So, certain types of sensors are used to measure certain physical phenomena. It's very important to note that when sensors convert this phenomena to an analog signal, the signal has certain characteristics. For instance, a signal from a thermocouple measuring temperature produces a very low voltage output. For instance, around plus minus 80 millivolt. Now, when the signal is transferred to a DAC device with a range of plus minus 5 volts, it's not able to take advantage of the full voltage range on the device, and therefore our measured signal will lose a lot of resolution. We'll talk about resolution later. So what we have to do is manipulate this signal so that it takes advantage of the full capabilities of the data acquisition device. Okay, so let's go to the step one, understanding your channel counts. So your test requirements or measurements may include a mix of signals. Signals could be current, voltage, on and off signals. It can also be mixed with sensors, thermocouples, accelerometers, strain gauges, and more. It could also include actuators like LEDs, motors, speakers, and many more. It may also include specialty I/O. Specialty I/O could be communication protocols such as serial, CAN, and other Modbus. So your data acquisition selection starts with sorting these into four different buckets. Arrange them into analog input, analog output, digital I/O, and specialty. Okay? So, for example, in vehicle data logging, meaning we are trying to acquire data from a car. Okay? So, many of the data acquisition systems will consist quite heavily of an analog input because we're acquiring more of data. Usually, control comes later after you have understood your system. Okay. So, for example, in a vehicle data logging, you may have 12 channels of voltage, which is around 10 volts, 6 channels of voltage around 60 volts, and then some sensors to measure temperature, vibration, strain, and torque. And then you would have a digital input output, which is recording the number of repetitions per minute, revolutions per minute in your wheels. And then, of course, the the car computer uses CAN bus. Okay. Now that we've gone through the sensors and type of inputs, let's discuss what we call signal conditioning. Now, most sensors need some sort of external hardware in order to perform their job. For instance, RTDs or resistance temperature detector need an excitation current, and strain gauges need a configuration of resistors called a Wheatstone bridge. So the external hardware required by most sensors in order for a data acquisition device to appropriately read the signal is called signal conditioning. Now, in addition to needing external hardware, not all transducers produce a perfect voltage for a data acquisition hardware to measure the data. So the signal from the transducer could be noisy, right? Could be noisy or could be too small or too large for the range of your data acquisition device. But one key note here is signal conditioning is not always required. Okay? Now, if I can just compare it, no, to who's using Instagram. Instagram applies filters, right? When you use a filter, your face suddenly looks nicer, softer, you look more beautiful or more handsome, right? It's the same concept. I think Sir John Mark is laughing. Or you're agreeing, right?
I'm not on Instagram, but I'm curious on what TikTok can deliver, and I guess it's the same, right? TikTok has filters as well.
It's the same concept. In TikTok, the signal conditioning algorithms probably do some sort of filtering. This may be removing some noise, cleaning out the 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 image, right? It's the same concept. The concept of signal conditioning is optimizing your input so that you have what you want for the output. Okay? So for example, this noisy low level signal, if you pass it through a signal conditioning circuit or maybe an algorithm, you are able to get a filtered and amplified signal. So this way, you will maximize your uh, data acquisition device's resolution. Okay? So these are the four common signal conditioning for voltage measurements. Okay? So this could be amplification. So amplification is very basic for all of us. Amplification is used to increase a signal from a sensor that is too small for your data acquisition device to measure. That's why you increase the you amplify it. Okay, like an amplifier for your microphone. A microphone is basically an amplifier, right? Next is attenuation. It's basically the opposite uh, of an amplifier. This is necessary when the voltage range is higher than that of your data acquisition device. Else, your data acquisition device will break. Okay. Now, since noise is inevitable in the real world, meaning it's impossible to eliminate noise, especially when you have long cables, you have a lot of systems stacked together. It's often necessary to filter a signal in order to remove the unwanted noise from the measurement. So a common filter is a low pass filter. You're hearing low pass filter, right? So which technically this filters out all signals with a frequency component below a designated cutoff frequency. So it will only pass signals that are, below that. Let me just drink water. Okay. So the next is isolation. Isolation helps pass your signal from its source to the measurement device without a physical connection by either using a transformer, optical, or capacitive coupling techniques. So this helps reduce noise by breaking ground loops. It also is something I think you've been hearing this. It also blocks high voltage surges and rejects high common mode voltages, which protects both the operators and the expensive measurement equipment. Okay. Now, beyond filtering that should be done on any voltage signal, some sensors that provide a voltage signal require additional signal conditioning to take a quality measurement. Thermocouples are a great example. To take a strong thermocouple measurement, there are a number of signal conditioning techniques depending on the sensor type. You'll see that later. And this on the sensor you're using and the signal conditioning it requires. It might need amplification because it's very low, or it might need cold junction compensation. Okay, so without a high quality sensor and data acquisition device, you will be responsible for building and integrating an external signal conditioning circuitry by yourself. Okay, um, with I'll just share with you this. These are some of the conditioned input outputs that are available in the market already. Okay, meaning if you buy data acquisition devices, they already have built-in signal conditioning. Okay. All right. So step two. I mentioned earlier that you will need to understand the 3 R's of data acquisition. So here we are. Okay. Now, for each signal you need to measure, you need to know how precise your data needs to be, the amplitude of the signal you'll need to capture, and the frequency of your signal. This relates to buying a cell phone that is very very expensive, but you don't really need everything, right? So you're going to take the step of understanding your precision, signal amplitude, and frequency, so that you only buy what you need. Okay. So precision would mean you have to optimize the resolution. The signal amplitude would also mean you will fix the range of your device, and the signal frequency will match to the rate of your data acquisition device. Now, if you're not familiar with resolution, range, and rate, let's discuss them very quickly. Okay. So there are numerous considerations. These are the three primary: resolution, range, and rate. So basically, resolution governs how closely the digitized signal can represent the analog signal. Remember, we are trying to get an analog signal into a digital form, right? So on our graph, we have an analog waveform. So this is our original signal that we have acquired from a sensor. So to digitize this, we need to break the amplitude of the waveform into a number of steps based on the resolution of the DAC device. So the the ADC's resolution, or the analog to digital converter's resolution, describes the number of binary levels the ADC can use to represent an analog signal. or this is the granularity with which changes the signal in the signal measured. So to figure out the number of binary levels based on the resolution, you can simply calculate 2 raised to the resolution. So the resolution of my data acquisition device right now is 3. Okay? So 2 raised to 3. 2 raised to 3 is equal to 8. Okay? So meaning I am able to represent my signal around 8 voltage levels. Okay? So this is like 20, right? 10 to 10 is 20 volts, right? So meaning I can represent this in 4 different levels, in 8 different levels only. Okay. Now, while an ADC with 8-bit resolution, with 6-bit resolution is 2 raised to 6, which is 64 voltage levels. If you can see this, now I can replicate my original signal much better because I have a higher resolution. Okay? So we can see that increasing the number of bits of resolution gives a better digital representation of our original signal. Okay? But also remember, there's always a drawback. A higher resolution device is always more expensive than a lower resolution device. Okay? So just get what you need. Okay. Now, next is the range. So imagine we have an ADC with an input range of negative 10 volts to 10 volts. With an example of 3-bit resolution, this would allow us to represent 8 possible voltage values, right? Which means the minimum change we could detect changes in our analog signal is 2.5 volts. So there's a formula around that, but basically, uh, that's 10 minus negative 10 divided by uh, the number of divided by 8, which is basically 2.5. Okay, it would only take up part of the range of the ADC, so we would only be able to detect and represent 2 possible values. Okay, so it only utilizes 20% of the range of the ADC. So we can do 2 things to address this. As discussed previously, we could amplify the signal. So instead of just using 2 to 2 volts, we could amplify this to a range of 10 to negative 10 volts. Or we can change the range of the acquisition in software to 2 minus negative 2 to negative 2 volts. This would make your acquisition utilize of 8 voltage levels. So this gives us a significantly better resolution. Okay. Okay. Now, most DAC devices have multiple input ranges, so you get the full power of your analog to digital converter, whether you're measuring a voltage range of plus minus 10 volts or a range of plus minus 2 volts. Always, if you are trying to measure a range of data, you always have to select the higher one and the smaller one as well. Okay, the third one is rate. So a sampling rate is the frequency at which we measure the original signal. So when we convert our analog signal to digital, we must sample the analog signal at a certain rate to capture all of its characteristics. Okay, so let's say we're measuring the sinusoidal waveform. So a real world signal has infinite data points at any given time, but a DAC device needs to acquire only discrete points at a given time. Okay? So the rate at which our data acquisition device takes new sample from our waveform is our sampling rate. Okay? Or sample rate. Okay. Notice how the rate at which we sample drastically affects the accuracy of the representation of the signal. Okay? Right now, my sampling rate is 11 hertz, but my original waveform is 10 hertz. Am I representing my signal correctly? The answer is no, right? Now, okay, so now I'm sampling at 25 hertz. This is almost 2 times of my original waveform. Now I am somehow representing the period of uh, my original signal, but I'm not exactly representing the original signal. Now let's try to sample using 100 hertz, which is almost 10 times, which is 10 times basically our original waveform. Now we can replicate our signal in a much more efficient or similar looking signal. Okay? Now, so here's the thing. If you sample too slowly, you'll end up with a waveform that distorts the shape and frequency of your actual signal. This problem is called aliasing. Sorry. Are you hearing aliasing in your in computer games? There's anti-alias filter, right? It's the same concept. You see that, Sir John Mark? Like anti-alias
Yeah.
filter, right? So which means it's higher. It's making the sampling rate higher, so that your signal looks much better or your graphics looks much better. It's the same concept. Okay, but in exchange for power, it's more power consumption for your graphics card. But in this case, we are making our sampling rate higher so that we can have an accurate representation of our signal. Okay. So I think you've been hearing this theorem before. So this is the Nyquist theorem basically. Okay. So the Nyquist theorem states that you must sample at greater than 2 times the maximum frequency component of your signal to accurately represent the frequency of your signal. That's if you want to just get the frequency. But if you want to get the shape of your original signal, you must sample between 5 to 10 times greater than the maximum frequency component of your signal. So I would recommend you to sample at the minimum of 10 so that you get the frequency and the shape all the time. Okay? Which means, let's say your signal of interest is 1 kilohertz. Okay? What's the ideal sampling frequency? Should that be a question, Sir Joe Mark, so that they win something? Just kidding. So later. We'll reserve that for later. So 10 times, right? So your ADC sampling frequency should be 10,000 hertz. Okay, so that you can replicate your 1 hertz signal accurately. Okay, now there's a problem when you have multiple signals that are, let's say, one hertz, and your data acquisition devices, my sampling rate is 1000 hertz, 10,000 hertz. This already says that I can measure this 1000 hertz, right? But there are devices that have two characteristics. First is using a multiplexer. The second is a simultaneous sampling device. So what's the difference? So when you're using a data acquisition device that utilizes multiplexing, basically all your input will go into a multiplexer, will go through one amplifier or signal conditioning device, and through your ADC, which means the sampling rate is divided amongst all the available channels. Okay? So you will still have to divide your frequency, your sampling rate on how many channels that you have. So it's not as ideal as a simultaneous sampling device. So a simultaneous sampling device is basically you have a certain number of inputs, maybe up to channel 3 or 4 or 8. Each of these will go through one, or each will have their own analog to digital converter. Okay? So which means that if, let's say, my channel 0 is 1000 hertz and I want to sample it, then my ADC is 10 kilohertz, I would be able to do it here just by itself without having any issues. And each of these channels as well will have no issues. But let's say I have 10 channels in here that is 1000 hertz and my ADC is only 10,000 hertz, I will not be able to replicate my signal properly. Okay? So, of course, simultaneous sampling is the best, but it's also more expensive. Okay? So, consider this when you're creating your own system. Okay. So, just a quick recap. Uh, the first step in identifying your data acquisition device is to list out the channels that you need, sort them into different buckets, into signals and sensors, whether it's voltage, current, and then types of sensors. And then bucket them into analog input, analog output, digital input output, specialty IO, and communications. Step two is for each signal to be measured, know how much precision you need, excuse me, the amplitude of the signal, and the frequency of the signal. And then match these needs to the three R's of your data acquisition device: resolution, input range, and sampling rate. Okay, now this is just more to, improve your measurement quality. Uh, for as long as you've had the three R's, I think that's the very basic. The next few items will just be more to improve it. Okay, so the next question is, um, how much data will I stream across this bus? Okay, so a bus could be your Ethernet, USB, PCI, PCI Express, PXI, or PXI Express. So depending on the amount of data that you're passing through your data acquisition device or recording or streaming, this can help you identify it as well. Of course, the right now the best solution is Ethernet because you can use it for high waveform streaming up to 125 megabytes per second, and then it's also best for distributed measurements because usually factories would have Ethernet connectivity or network across the plant as well as portability. All right. So the next question is also, how will you connect your signals to your data acquisition device? Some would have screw terminals where you just have your wire and screw it to lock it in. You also have BNC terminals, which are more robust, more reliable, but somehow a little bit more expensive. The third are connectors or VHDI, which basically terminal blocks that allow you to connect your signals and shield it properly. Okay. The third question is, where will you take your measurements? So measurements may not be always in the laboratory, right? So some data acquisition devices may need ruggedness. Ruggedness could be in field environments. Okay. So first is the laboratory environment. You don't need any ruggedness. In hangars or in large laboratories, you may need dust resistant, temperature resistant. In outdoor field environments, you may need dust proofing, waterproofing, shock and vibe resistance, and temperature resistance, and so on and so forth. So these are some of the questions that you need to ask. So some manufacturers, just like this that you're seeing on the screen, like National Instruments or NI, they have a range of data acquisition devices that you can use for different types of environment. So it's the same scenario earlier, right? Why would you buy a phone that is waterproof when you're never going to be in water, or you're never gonna be in a situation where you're, let's say, gonna dip it a long time in water, right? So in similar concept with data acquisition, if you're always in a safe space like in a laboratory, you just get the least rugged device. But if you're always on the most rugged, always wet, damp, uh, dusty, you can choose the rugged devices. There's for different applications, there's different solution. Okay. Now, we've pretty much talked about hardware, but this solution will not be complete without the software. So let's quickly talk about software before we provide the demonstration. So, there is a cost associated with every measurement application. Now, for PC based data acquisition applications, the obvious cost is the price of hardware and software. But there's a big but. What many don't consider is the cost of development that goes into making this application, right? Visible price when we do a project is how much is the software, how much is the hardware. But the hidden cost is the development cost. Okay? Based on a survey, usually the hardware and the software price is only 36% of the total cost of the project, while 64% is the total measurement application cost, or the development cost. So this is why software is important, because it can allow you to expedite the cost of the development, as well as provide scalability and long-term maintenance that will reduce your cost of development. So here are some options that you can use, right? So there's application software. Usually, application software is ideal for starters. The reason behind is you don't have to program as much as you need to. You can just connect your device, select some settings, drag and drop, and then configure this a little bit, and you're done. While some applications or some engineers would use programming languages like C, C++, C Sharp, Python, MATLAB, Visual Studio, Measurement Studio, and LabVIEW. The question is why? You would use this programming language if you want to have a complex and customized applications. So this is where programming languages shine. But of course, it requires more experience, more training for you to be able to implement this. Each of these programming languages have a learning curve, um, and each of this matches a specific type of persona. Just like me, I'm a visual learner, I'm a visual thinker. That's why I'm more geared into using LabVIEW. And this is what I'm going to demo to you today as well. All right. So yeah, so there are multiple programming environments that you can use, but today I'm here to share with you that LabVIEW allows for easy transitions from configuration-based measurements to graphical code. Okay, so you can also communicate with your data acquisition devices with text-based programming languages using C, C Sharp, Visual Basic, .NET. So it really depends on what you want to do. But today we are going to share with you using LabVIEW. Okay, so let's build a DAC system. Let's put all the pieces together. Now, you've already been familiar with understanding your channel counts. So first, when you're starting up a system, make sure that you understand the output that you want to have. The overall acquisition that you want to make, and then identify your sensors and signals, and then bucket them into different types of analog input, output, digital input, output, and specialty. And then once you know those data, you now dig in deeper and understand what resolution you need, what range you need, and what rate you will go through. And then if you really want to improve your signal, then ask these, like, what bus is right for my test? Where will I be taking my measurements? How often do my test needs change? So if you're able to answer this, or actually, if you're starting to work on this kind of activities, you can also work with me, and I will ask you these questions so that we make sure that what you're trying to do is just is we will just choose the right equipment for it. We're not going to choose like a super expensive equipment to do a simple test, or maybe a super complex test using a super simple equipment. This is where customizability and knowledge comes together. All right. And the question there is, how are you going to implement this through software? Now, before we do that, I would like to introduce you to LabVIEW. Okay. So LabVIEW is a graphical programming environment. So once you've identified your inputs, your outputs, you identify how your program will flow, right? So for example, this acquisition, you get your user input, wait for a trigger, start to initialize your program, and then loop it maybe 100 times, acquiring the data that you want to acquire. And then by the end of your program, you send an email notification. So typically, programmers would start developing this. Okay. Now, the beauty about using LabVIEW is when you program, you actually can program the way you think. So a code in LabVIEW would look like exactly a flowchart. So you can see the flowchart looks like this, but the graphical code looks like this. So the input is here, the trigger is here, the initialization stage is here, and then the loop or the program to acquire the data from your acquisition device is like this. And then maybe send it to an email server later on as well. So, as contrast to text based programming, each would be sequential. You'd be using text based. I'm not saying one is better than the other, but for people like me who are more visual, more as a visual learner, uh, this is much better for me. Of course, there's always a learning curve, but let me share with you some of the most, the better features of LabVIEW. Okay. Uh, okay, maybe. So with LabVIEW, you can quickly create professional interfaces with built-in. So you just have to, most of the programming in LabVIEW, you can just right click and drag and drop. That's basic how we think. It's very intuitive. With a simple drag and drop, you can create professional user interfaces. The thing about LabVIEW as well is you can use it to connect to all of your hardware, not just the hardware that NI provides. It can, of course, connect to third party hardware. In fact, when most of the manufacturers of instruments like oscilloscopes, function generators, DMMs, they create a LabVIEW driver so that users can connect it directly to their hardware. This is how much the industry has adopted using LabVIEW for many third-party manufacturers to create a driver for their instruments. Okay, so as we have mentioned, when once you have received your data, the user's idea is to visualize and understand your data. So you can use built-in drag and drop to immediately visualize, and most importantly, to analyze using Fourier transforms, comparisons, and other algorithms that may be complex. There are also tools within LabVIEW which you can use to bring in MATLAB code so that you can leverage its much more powerful mathematics capabilities. There are also built-in uh, code that will allow you to connect it with Python. So if you are considering using a graphical programming environment such as LabVIEW, I think the question that will always come into your mind is, can I actually leverage LabVIEW to use all of my previous code? The answer is yes. You can reuse IP or intellectual property code from different languages. You can bring it into LabVIEW so that you don't have to create it all over again. Okay. Now, so let's program a temperature measurement system. Okay. So this is what I just said just now. So with LabVIEW, you can connect it C Sharp, MATLAB, C++, Python. Okay. Uh, but before we do that, let me give you a LabVIEW introduction. Okay, so this is LabVIEW basically. In here, I will create a LabVIEW project. So this is where we'll spend our remaining time. Okay, so in LabVIEW, I'll create a project that can, just store my, the project we're going to create. So here you can use it to organize your system. You can put your VIs here. A VI is your code. Okay, so a VI is virtual instrument. Okay, so what is a virtual instrument? Okay, so let's put it here. Okay, so when I create a VI, you can see there are two windows that pop out, right? One with the grid and one with the empty. Okay, so let's call this. Okay, okay. So this is your graphical user interface or your front panel, while the one, so this is your front panel, while the one on the right is your block diagram. So let's save this one first. Okay. Uh, Digital creatives. code. Okay, so it's saving as a VI. So it's called a VI, virtual instrument, because it replicates the function of the physical instrument. Okay, all right. So in the front panel, this is where your graphical user interface is. So what I'm going to do is right click here, and then I can select, controls, indicators. Okay. So for now, I'm going to give you a basic code that you can do, right? So I'm going to input a numeric number here and then drag it down. Okay. And then I'm going to have a numeric indicator. So let's do a very basic addition. Okay. Right. So what did you notice when I place something on the left side of the screen? You notice that there is also something that's popping up on the right side of the screen. So this is actually connected to the right side of the screen. Block diagram. Okay? So I want to create a code as simple as A plus B is equal to C. Right? A plus B is equal to C. Now, how am I going to implement that in code? Okay. So this numeric control has a terminal right here. This terminal has an output that will will feed out the data that's coming from here. Okay. Now, in order to implement a addition function, I'm going to right click and then find an algorithm that I want to use. For example, addition. But I can also use the what I mentioned earlier, the built-in analysis functions that is in within LabVIEW, like basic mathematics, okay, or even complex Boolean, even put in strings, or even comparison. But for simplicity's purpose, I'll just place a addition. So what I'm going to press now is Control H. Okay. So right here, we can see the context help at the upper right of the screen, right? So what it says, the basic concept of a node, this is a node, right? This yellow thing is a node. This node will only operate once the required inputs are available. So if you look at the context help, right? A required input is something that's bold. So X is bold, Y is bold, right? So in order for it to output data, the inputs must be available. So how do I do that? I'm going to put my mouse here, click it, and then connect it here. All right. And then with B, I'll connect it here, and there you go. And then the output of this will be C. All right. Okay, so let's try to run it. Okay, before we run it, I'm gonna show you something here. This is the This is the panel tools palette. So if I press run, my code will run, and then there are other functions here that we'll not discuss today. But if you want to, we can talk about it some other time. But basically, what I want you to look at is this run button. Okay, if I remove this, nothing changes, right? But if I remove this, you will notice that this turns to a broken arrow because this node has no input to it, right? If I click this, an error panel will come out and says add contains unwired or bad terminal. Now if I show error, it will point it here and tell me, oh, there's a problem there. So just with that, it's already telling you where the problem is so that you don't have to manually find it. Okay. So if I look into this, it will say, X is a required input. So I just have to wire this out. Okay. Now I can run my program without having any issues. But I will have, I will not see the output in C because it's not wired. Okay. Now to show you that, I'll do a very basic 1+1. Okay. So if I run this, is C gonna have an output? The answer is no because it's not wired. Okay. But if I wire this out, 1+1 is equal to 2, right? Just by connecting this, I am able to get the output of this mathematical formula. All right. Is that clear? So that concept is called data flow. So to show you data flow, I'm going to click this highlight execution. It's one of the debugging tools that is used in LabVIEW. Okay. If I press this, LabVIEW will show me how the data will flow into my code. All right. So if I press run, have a look. There you go. You see, plus will only output once all of the inputs are available. Let's try that again. Okay. So A plus B is equal to C. This will never output if these two items are not available. Now, LabVIEW operates in a multi-threaded environment. So it's not operating based on the length of the lines. Okay. It's not operating by the length of the lines. It's operating in the background. This is just only showing it to you graphically. Now, uh, I'm going to give you a more complex code. Let's try what's in my program. Let's just see my program. Hmm. Let's try to formulate this code. A plus B times C divided by D minus E. So first, what I'm going to do is I'm going to create more numeric controls, naming it C. I can just drag and drop this by pressing Control and naming it to D and then E. Okay, and then our output is output. Okay, now how are we going to implement this code in LabVIEW? Okay, so B times C, right? Let's remove everything first. Okay, B times C. So what I can do is if I know the function that I'm trying to get, I'm going to press Control space and then say multiply. Okay, this multiply. I'll connect B times C. Okay, now I want to do D minus E. I can also right click and do subtraction. Okay, D minus E. Okay, good. So what's next? I need a division. Okay, division. Okay, get ready because there's an upcoming question. All right. So, uh, how to do this? Okay, A plus the output of B. Okay, make it, just make this B times C. Okay, and then the output of A plus B times C will be divided by D minus E. Okay, this formula is this formula. Okay, so again, the rule here is that a node will only operate once the required inputs are available here. Okay? Okay, sana naintindihan niyo siya. So let's try to do a simple uh you can do it with your calculator, no? So 2 plus 2 times 2 is equal to what's the answer that? 2 plus 2 times 2, 4 plus 6, okay, divided by 2 minus 1. 1. Okay? Anong sagot? Hindi yan yung test. Okay? So the answer there is 6. Because 2 plus 4 divided by 1 is equal to 6. Okay? So, is the formula correct? Right? Tama ba? Okay. Okay. Any questions? So this is what we call data flow. A node will only operate once the available or once the required inputs are available. Okay. Now, walang questions. Sige. Okay. So I think we can just go through about it. I think that's the basic of LabVIEW, right? What you're seeing right now is very basic. It's just mathematics function. But if you want to make it a little bit more complex, let's try it out. This is more of a demonstration rather than, you know, browsing it very quickly. Okay. My camera died already. Let me change to a different camera. Okay. Now I have a webcam na. Okay. Um, so let's take it out. Now what I want to do is the measurement. Okay. A temperature measurement. Okay. What I will do is place this thermometer right here. I will also put a LED. So an LED could signifies it whether something is alarming. I will also put a graphical chart to show the historical plot. I will also put a stop button right here. Ah, and I will also put a numerical control, probably a knob. Okay, knob. So this is the last part of our session. Okay, I will name this threshold. Okay, uh, let me just, sorry, very quickly. Let's put everything here. Oh, never mind. Okay. Okay. Now, so what you're seeing right now on the screen is just user interface. Okay. It's just user interface. It's not actually doing anything yet. Okay. Now for it to do something. Sorry, Sir John Mark, can you just briefly focus on the camera? Yeah, yeah. Right. Okay. So right now, yeah, there you go. I have this data acquisition device. So this data acquisition device, we're not gonna go through the specifications anymore, but basically, not sure if you're seeing it properly. It's not focusing right. This is a thermocouple input device. I have a thermocouple right here, which I will touch later. This is a data acquisition device with 16 channels, 24-bit thermocouple input. So inside this, it has a an analog to digital converter and a signal conditioning device specific to thermocouple input. Okay. Now I'm connecting this to this chassis, which is connected to my computer via USB. And I'm going to acquire data from this to the computer. All right. So let's just put it back. Sorry, it's shaky footage. Okay. Now in LabVIEW, there are different ways to do that, but I will show you the fastest way for now. Okay. So in my block diagram, I will go to Express. So this is going to be an Express BI. I will go to Data Acquisition Assistant and place it in the block diagram. Now with this one, it will help me configure my data acquisition device using drag and drop functions. But if you, of course, want to have a more complex data acquisition or more accurate, you can definitely do that manually. So what we want to is acquire signals, an analog input, a temperature, and a thermocouple. Right. So I have previously configured this to be named. Let's change this. Okay. So this is what we call the Measurement and Automation Explorer. I can change the name of my device from here, but because I have so many things open in my computer, it's not taking it so well. Let's skip that part. But I've previously named this uh, temperature measurement for Nexperia because I also did this demo one time. Okay. And then I know that my device is connected to analog input 0. So let's click finish and let's configure it. Okay. Now we've talked about earlier something about range. So that so we can we adjust the range so that we can maximize the resolutions, right? I know that my room is somewhere around 16, 17 degrees. So the minimum should be around 15 and maximum should be around maybe 30. Okay. Celsius is, units could be Celsius, degrees, Kelvins, or what's R? I don't know. And my thermocouple type is J. Okay. Now I want to acquire continuous samples, and samples to read would be 100, and I will do 1,000. Okay. Try to run this. And sorry, Sir John Mark, if you can just show me the camera very quickly to show them I'm touching it on the screen. So as I'm touching it, you can see the number rise here. It's not still yet in the code, right? But you're seeing it here rise, and it will fall as well as it goes down. So this is the configuration part. Now what we want to do is implement this into a code so that we can visually see and analyze this code. Okay. So it's building it in the background. So it's gonna be creating a loop around it because it's going to acquire the signal multiple times. It's taking quite some time because we're streaming. The resources are not so much available. Okay. All right. So now we have this loop. If you're programming before, you're familiar with a while loop, right? A while loop will only stop if a specific condition is met. And in this case, that condition is if you press the stop button. Okay? So the stop button of the code that was created is quite ugly. It's pretty old. So I will delete this. Okay? And then I will replace it with this better looking signal. So I just wire this to the stop button of this code. I can actually expand this one just to show you that you can see it much better. Okay. Now, first, let's acquire temperature. So this device is actually a driver configuration of the actual system, right? So this is getting data from my sensor. First, let's get the data to the thermometer. Okay. So this is the thermometer, right? Okay. Let's change the value of this to third, let's say 33 and maybe 15. Okay. So that I only have this range. I don't need up to 100. My room doesn't go to 100. That's so hot. All right. Right. So I'm running. Okay. Notice how my system is running, right? It's acquiring very slowly because I've turned on the highlight execution. Uh, if you turn on highlight execution, it will be very, very slow. So in order to stop that, okay, let's stop it first, uncheck it, and then run. Mm, Something's running with my code. Okay. Let me just refresh this very quickly. Let's try it again. Okay. I did something wrong because of that highlight execution. So I just need to clear the buffers. Try that again. Okay. Should be running. Okay. Okay. Yeah, so it's actually acquiring data. I'm just so stupid because I thought I was connecting the chart. So right now, if you can turn on the camera, Sir Joe Mark, uh, if I touch this one, my code is actually running already, right? So if I release it, the temperature is slowly going down. But if I touch it, it's slowly going to rise. Okay. Now, what we want to do is connect it to a chart. So I'm going to put the chart in, connect this wire to the thermometer as well so that you can see it as well. Okay. In the chart, right? So now that you're seeing it with the chart, it's slowly rising up if I'm touching it. Okay. Now let's make our system a bit more complex. Let's say if I meet a specific threshold, let's say my room is already so hot, okay? I want to turn on an alarm, okay? So what do we do? I will right click and then get a comparison function, okay? Place it here. Now, this function will say if x is greater than y, a boolean function or a true or false will come out of here. Okay. So let's say the threshold is from 15 to 33 as well. If I set the threshold to, let's say, 30, this boolean control should turn on. Okay. Let's try it out. So it's reaching 30. Okay. So Sir Jomar, can you just full screen the code instead of me being bigger? Okay. So if I release it, it's less than 30. The boolean function will turn off. And then if I touch it and it goes beyond 30, it will turn on. So in a matter of a few minutes, we were able to create such a simple code, but we are already able to create a smart system that allows us to identify the temperature of the room or the temperature of what you're measuring. This could be an oven for burn-in test, or for, when you're manufacturing any product. And then when it reaches a certain temperature, you can turn on a fan, an aircon, or any cooling device or any heating device, so that you can control your system. Other customers use it to monitor the process of an oven, how it's heating up, what's the temperature, what's the temperature. So one of the things customers do is log this data. So when you log this data, you actually are able to know the history of your data. So how do we do that? We can try to write to measurement file. Okay. So we can output it into an Excel sheet. For simplicity purpose, I'll just connect it very quickly. And so I'm going to get the output of this data and then put it into the signal. All right. So let's run it. Okay. So currently the temperature is 23, right? Now I want to touch it. Okay. Is it running? I don't think my computer has enough memory. Okay. Let me just stop it. Yeah. My computer doesn't have enough memory right now. Let me close some of my applications first. Okay. All right. So now it's slowly increasing, right? Okay. It's reaching the temperature. Okay. Then let's just stop it. Now I can open up the Excel sheet where this guy was writing to. Now it's 8:52 p.m. It's almost time for sleep. Let's just open this up. Mhm. Open. So you can see here that My computer is very slow. No, it's just okay. So you can see that the data is being logged here. From here, in an instant, almost in an instant, but the temperature was logged from 25 to 30 in a matter of few seconds. So imagine what you can do in programming if you're using a graphical programming environment. You don't have to memorize a lot of stuff. You just have to familiarize yourself with how the graphical programming environment works, and you should be able to extract and create code uh, while basing it on your flowchart without having to create long lines of code. The best thing about it is you can use built-in signal processing functions, mathematics functions, data communication protocols, and debugging tools so that you can make sure that your system, your code can run uh, as optimized as it can. Now, LabVIEW itself, if you want to take the training, the official training of LabVIEW takes about 5 days. For 5 full days, like 8-hour training days, um, because it's that, it's a programming language. It's still, it's graphical. I'm not saying it's easy, but it's relatively simpler than text-based programming. And if you want to establish codes or more complex code, then I would recommend you to take that. I think LinkedIn Learning has some basics training, but I can also provide that as well. All right. So, any questions around this one? I think we're nearing the end of the session. Sir John Mark?
Yep. Is
Yeah. So,
anyone from our participants interested in asking questions?
I know it's so hard to ask questions while you're live, right? Okay. Yep. Yep.
Anyways,
Yeah, yeah, sure. So yeah, that's it. That's a demonstration for LabVIEW data acquisition. We cannot do a more complex demonstration because it will take so much time. But I hope this can get started. At least knowing how to pull out controls, indicators, and creating a simple code out of LabVIEW. I can definitely uh, create a more complex system later on. Okay, so with that, I'd like to continue just to end my session. Uh, yeah, hopefully that is a good use of your week night time. I'll just very quickly share who I work for right now. So again, my name is Lorenz Yatco. You can reach out to me on this number or on this email. I actually work for Braymac. Braymac is a component distribution company, but we also provide test and measurement equipment such as National Instruments or NI. So my company is actually based in Sydney, Australia. It was founded in 1984, and our annual revenue is around $290 million. Um, Pramac only has a few people around the world, which is about 218 people. We do have in-house design capabilities. So in the Philippines, I'm the only one here. There's also one engineer in Thailand, Malaysia, Vietnam, and our headquarters in ASEAN is in Singapore. While in Australia, we have about 100. Australia, New Zealand, we have about 120 people. So this is our global operations. Now, one of our solutions range from components. So if you are looking at any of these systems, we can definitely provide it to you, like Renesas, InnoDisk, uh, and and so on. All right. If you're also interested to know what else we can provide, if you're a design engineer, looking for components, looking for alternative sources or for cross references, we can provide interconnects, passive and discretes, embedded modular devices, and electromechanical like switches, relays, uh, and then power and battery. So yeah, we have a full range of extended solutions. If you are looking at even up to touch panels, sensors, diodes, oscillators, we can definitely supply that to you. So feel free to reach us out on the email provided, and I can definitely help you. And just don't forget, you can we can also talk about photography later on if you're ever interested. So that's it. Thank you so much, Sir Jomark, and thank you for those who have attended this session.
Have a great night. Have a great weekend.
Thank you.